The Enigma, that is the sum of two squares, which states that every prime of modularity for n plus 1 can be written as a sum of two integers squared, and the Pretence, that is, the Windmills of the mind. My motto: plain honesty, simple truth, easy understanding, the joy of finding things out for yourself. The simpleton's mathematical coat of arms. In Euclid we trust, and not the mathmagicians. So what is the enigma of the sums of two squares? Well, take the number 34 and it relates to the sum of two squares. Take 77 and it does not. Take 73 and it does. Take 33 and it does not. Take 37 and it does. Take 74 and it does not. Take 76 and it does. Take 32 and it does not. The numbers are, to say the least, random and totally unrelated, and yet relate to the sums of two squares. That 3 of the 4 numbers are themselves sums of two squares is coincidental and separate from the enigma, as is evident from the fact that the factors of 76 are not what one would expect to relate to the sums of two squares, and being equal to the sum of two squares would occur less and less frequently as the numbers got bigger. There would be no way to decide which was which except by what is to follow. 1. Take the quadratic equation y equals minus x squared plus x plus c. Then input x equals 1 to n, whatever y is positive for any given c. For c equals 33 and 34, we get the following results, which we feed into the equation f of z is equal to 4y plus 2x minus 1 squared, which results in the following two tables of results for 33 and 34, from which we see that only 137 is equal to the sum of two squares, which are 4 squared plus 11 squared. 2. Take the quadratic equation y equals minus x squared plus 0 plus c, then input x equals 1 to n, whatever y is positive for any given c. For c equals 33 and 34, we get the following results, which we then feed into the equation f of z is equal to 4y plus 2x squared plus 1, which results in the two tables of results for c equals 33 and 34, from which we see that 133 is not a sum of two squares, since its factors are 7 times 19, which are both 4n plus 3 primes, and only 137 is equal to a sum of two squares, which is equal to 11 squared plus 4 squared, but is also found to be equal to 10 squared plus 6 squared plus 1 squared. What we have discovered is that if p to the 4n plus 1 minus 1 is a sum of two squares, then p to the 4n plus 1 is also a sum of three squares, one of which is 1 squared, in which case p to the 4n plus 1 is equal to a squared plus b squared plus 1 squared. One can conjecture if there are infinitely many of them, but it is not really worthy of consideration, unless of course one is short of better ones to justify themselves as a mathemagician. 1. What we have done on the previous two slides is to tabulate the steps of the algorithm that one would use to find the sums of two squares of a number, which is a. Take the integer square root of the number. b. Subtract the square of the root from the number and test to see if the remainder is a perfect square. c. Let root equal root minus 2 and repeat b until root less than 1. 2. In his video, Why Was This Simple Visual Proof Missed for 400 Years? Fermat's Two Squares Theorem, mathologer makes what are for me some contentious and pretentious changes to the colouring of the centre hub of the windmills shown on the next two slides in support of Zagier's one sentence proof. It's just plain tosh. Here are the 4 possible windmills for this small 4n plus 1 prime 53, which I chose so as to make the graphics manageable. The centre hubs are all odd number squares. Had I started with the 4 arms of length 12 instead of 13, there would have been no perceptible difference except for the last diagram, which would not have had the 4 unit arms attached and would have just been the perfect square of 7. On this slide, I have repeated the exercise, but for the centre hubs equal to an even-numbered perfect square. In order to do this, I have subtracted 1 to give a number of modularity 4n as per slide 5. Notice that like 137, we find 53 is also equal to the sum of 3 squares. If we replace the columns of unit blocks by single straight lines as shown, and join the 4 corners by straight lines to form a square, we obtain identical diagrams as shown for both the odd and even centre squares. The inset shown has been extracted from God Invented the Integers and edited by Stephen Hawking, and shows that the diagram we have produced is a proof of the Pythagoras theorem, which is given on the next slide. Proof of the Pythagoras theorem. Taking our diagram, which we have labelled C, B and A, the centre square is equal to A minus B all squared. Therefore, C squared is equal to 4AB all divided by 2 plus A minus B all squared is equal to 4AB all divided by 2 plus A squared minus 2AB plus B squared, where we see that 4AB all divided by 2 is equal to 2AB. Therefore, they cancel each other out to leave us with C squared equals A squared plus B squared, QED. To conclude, I see nothing in what I have done in the latter half of this presentation that points to anything that could be construed as a proof of the sum of two squares theorem. Well, actually, I am totally wrong, as the proof is staring me straight in the face, and I have only just seen it. Taking our Pythagoras theorem proof, C squared is equal to 4AB all over 2 plus A minus B all squared. Therefore, C squared is equal to 2AB plus A minus B all squared. And replacing C squared with A squared plus B squared, we get A squared plus B squared is equal to 2AB plus A minus B all squared, QED. So every step in our algorithm for unraveling the sums of two squares is a solution to the Pythagoras theorem, except that one term will be an irrational, root squared, if both are not an integer, and applies equally to 133 as well as 137, hence no discernible difference in the algorithm or diagrams.